Things to come.
Take man into space. So, to set the stage for the part the rocket will play in the coming conquest of space, our artists have searched back through history and traced the rocket and various space travel ideas from their earliest beginnings. The first thing we found out was that the rocket is not such a modern invention after all. Early inventors soon realized that steam rockets would be too heavy to fly, so they returned to designs utilizing gunpowder. These ideas made many successful flights, on paper. In 1865, Jules Verne fired the imagination of the world with his first book on space travel. It was called From the Earth to the Moon. Mr. Verne used a very interesting device in getting his heroes to the moon. He shot them through space inside an enormous artillery projectile. It was Verne's story that inspired George Méliès to create the first space travel motion picture in 1902. To have the rocket pull the ship instead of push it. This conception was quite unique, but only an inventor's dream. However, a few decades later, a real milestone in rocket history was passed when the American professor, Robert H. Goddard, introduced a liquid fuel rocket, which used gasoline and liquid oxygen instead of gunpowder. This small forerunner of our large present-day rockets actually rose 60 feet into a wintry New England sky. He wrote, "Theoretically, there is no limit to the size of a rocket which uses liquid fuel." In 1929, Oberth designed a giant rocket ship for the Fritz Lang movie, Frau im Mond. The Girl in the Moon.
Oxygen here. When burned with a fuel, in this case alcohol, it produces an intensely hot, torch-like flame that would quickly melt the motor. However, we cool the motor by first circulating the alcohol fuel around it, until this fuel finally reaches the point where it is sprayed, along with the oxygen, into the combustion chamber. When this steady flow of alcohol and oxygen is ignited, it produces a continuous explosion which blasts the rocket away in the opposite direction. Here again we have action and reaction. If this motor is placed in a streamlined hull with suitable controls, it can reach a high altitude in a very short time. The V2 rocket motor only operates 65 seconds to a height of 20 miles. But then the V2 has gathered so much speed that it will coast upward to an altitude of 114 miles before gravity begins to pull it back to Earth. Notice that the rocket does not nose over in the thin upper air, but it falls tail first until it re-enters the denser atmosphere where the air, acting on the tail fins, turns the rocket nose down. Early in 1949, space history was made when the payload in the nose of a V2 was a small rocket called the WAC Corporal. When the large V2 reached its maximum speed, the smaller rocket was ignited. This additional boost in speed enabled the WAC Corporal to set a new high altitude record of 200 in its launching position. The first great blast starts to lift it, and after gaining initial speed, the first section is cast off at 20 miles up. At 45 miles, the second stage is released. The third stage now fires until it reaches an altitude of 70 miles. At this point, our rocket has now attained a tremendous speed and the motor shuts off. Its forward momentum would carry it straight out into space if it were not for the Earth's gravity. This downward pull of gravity bends the upward course of the rocket into a curved path. And if the rocket's speed going away from the Earth creates enough centrifugal force to balance this pull of gravity, our rocket will continue coasting in its curved path around the Earth. The rocket will have to go nearly 16,000 miles per hour and will make a complete trip around the world every 2 hours. A few adjustments in its course will be necessary, but this can be accomplished from the ground by remote control, after which the rocket will scientific apparatus contained in the satellite. A mirror will focus the intense rays of the sun onto a silicon battery, converting solar energy into electricity. There will be a television camera to give pictures of the Earth as it appears from 1,075 miles up. We will collect very important data on the effects of the mysterious cosmic rays. Even hits by meteorites the size of a grain of sand will be recorded. Every 2 hours, when the rocket moves over the North Pole, its radio will transmit a stream of data to a receiving station below. This will be the first outpost in man's conquest of space.
We must plan intelligently if these pioneers of space are to survive and return to Earth safely.
First, we would design and build the fourth stage, and then tow it into the air to test it as a glider. This would also allow the crews to practice. Next, low-altitude flights would be made, firing the small rocket motor in the fourth stage. This would also give the crew more and more training. Following that, the third and second stages would be constructed and tested very thoroughly on the ground, after which they would be joined to the passenger section so that faster and longer flights could be made up to speeds of about 12,000 miles per hour. The only thing remaining would be the building and ground testing of the huge first stage. Then there would be no more test flights. When all the sections are joined...
There it is, a small atoll of coral islands in the Pacific, where man is dedicated to just one cause, the conquest of space. Here below us, a small city has been created to house the scientists, engineers, and technicians on whose shoulders rests the tremendous responsibility for this great adventure. This is the Rocket Assembly Building, with tracks running to the launching site. Only 48 hours remain until firing time. Our spaceship moves ponderously toward the firing site. After the ship is securely anchored over the blast tunnel, the elevator's spar is raised into place for the final pre-flight check and fueling. This is the blockhouse, the control center for Operation Space Flight. Here, the oscilloscopes, radar scopes, computers, and tracking devices are the brain and nervous system for the rocket. Dancing patterns of light will record every detail of the blast-off and climb into space. In the windowless blockhouse, observation is by periscope. Through a system of worldwide radar stations, electronic eyes will always be focused on the rocket as it orbits around the globe every 2 hours. The tracking radars report ready and are standing by. The optical tracking stations are poised and ready to follow the rocket in its upward flight. As 0 hour approaches, the painstaking work of the checkout crew continues. The ship and every piece of its equipment is being checked and rechecked.
Blockhouse, can you hear me? Will you give me that stage 2 separation signal again? Okay now, over. Swivel motor, stage 3 to pitch right. Okay, now give me the left.
Attention all personnel. It is now X minus 2 hours. Fueling crew, take your stations. Safety area will be cleared by all personnel.
In the pits, the required quantity of fuel is preset. The pumps will deliver 1,230 tons of hydrazine and red fuming nitric acid into the tanks of the waiting rocket. It is now X minus 20 minutes.
Flight crew, report aboard rocket. Flight crew, report aboard rocket.
After years of careful preparation, testing men and materials, this is the final payoff. Now, man will bet his life against the unknown dangers of space travel. Human reactions are not precise enough. Therefore, once the launching timer is started, the entire takeoff and flight into outer space will be controlled automatically.
X minus 5 minutes. Clear the firing area. Clear the firing area.
X minus 90 seconds. X minus 30 seconds. X minus 20 seconds. X minus 15 seconds. X minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
The total firing time has been 5 minutes. The ship will now coast for 51 minutes before the adaptation maneuver begins. At over 60 miles above the Earth, the crew members experience the sensation of weightlessness for the first time.
Blockhouse to XR1. Your cutoff altitude is 63.9 miles. Distance from launching pad, 705 miles. Velocity, 18,467 miles per hour. Angle of elevation, 4 minutes of arc. Plane of your ellipse of ascent incline, 66 degrees, 32 minutes, 2 seconds to plane of equator. Out.
51 minutes later and halfway around the world, the rocket is coasted to its maximum altitude of 1,075 miles. Its speed has diminished to 14,770 miles per hour. The navigator must now take a bearing on 2 fixed stars. He will line up the ship for the adaptation maneuver, which will drive it into a circular orbit around the Earth. Electronic controls will fire the rocket motor at the exact second the ship reaches the proper position. The ship and crew are now coasting freely and silently through space. Here, man is no longer earthbound. From his new vantage point of over 1,000 miles high, he sees the Earth as a vast rolling sphere, upon which the oceans and continents are reduced to simple patterns of light and dark. Great cloud formations will appear as small patches of snow. Evidence of man's existence is almost invisible. Large cities can be seen only with the aid of powerful optical equipment. Meteorologists will make studies for long-range weather forecasting. The science of astrophysics will welcome the clear views of our moon and planets, unhampered by atmospheric disturbances. Space medicine will benefit from tests conducted with new type spacesuits.
Air Force Keflavik Iceland calling XR1. We have you in radar contact at 107 miles due south of station at 29. Estimate you at Prestwick Station, Delta at 37.
Tests and observations by the crew will lay the groundwork for the future construction of a space station and will add to our knowledge of many sciences.
Instrument rocket approaching from 3 o'clock high.
At a pre-calculated time, the rocket's path will cross that of the instrument carrier, sent into space a few years before. "22 hours after takeoff, our spaceship has made 11 revolutions around the world. It is now time to make the return trip. The engineer releases the third stage. It'll be left circling in space. All tests are now concluded. The navigator checks the ship's position for return firing. 1 minute to go. The automatic firing timer is set. The ship is lined up so the blast of the motor will be against its forward motion. This will slow the rocket's speed and cause it to begin its long glide back to Earth. The ship is now moving 1,000 miles per hour slower. After coasting halfway around the world, the rocket will leave the vacuum of space and sweep into the upper layers of the Earth's atmosphere, where air friction will gradually reduce the rocket's speed. When the ship drops to an altitude of 50 miles, air pressure will build up on the control surfaces. For the first time in the entire flight, the captain will be able to fly the rocket as a normal plane. Air friction begins to send the skin temperature of the rocket climbing until the ship glows cherry red at 1,350 degrees. The double hull and refrigeration keep the crew from perishing. The returning rocket continues the long glide down into the lower atmosphere, its temperature gradually dropping to normal as airspeed diminishes. Mission completed. Man has taken his first great stride forward in the conquest of space. His next goal will be the exploration of the moon, then the planets, and the infinite universe beyond.